our next podcast on solubility, we'll touch on the solubility rules that we've seen previously and then add some more components and some more vocabulary terms into that. Solubility can be defined as the amount of solute that dissolves in a given amount of solvent at a specific temperature. And when we get to our podcast on factors that affect solubility, you'll see why we mention a certain amount of solvent at a specific temperature, because once you start to change those amounts, that changes the amount of solute that can be dissolved. So we measure this, or we describe this mathematically as the grams of solute usually per 100 milliliters of solvent. So if the amount of solvent isn't given, we assume it to be 100 milliliters. Otherwise, we would just plug in the amount of solvent that we were given in the problem. So you've covered solubility rules. You've used them before. We're not going to go into how to use this table that you've seen before, but I just wanted to review. So what we're going to add to that knowledge, so besides being able to look at an ionic compound and determine if it's going to be soluble or non-soluble or insoluble, we're going to add to it this term, this phrase, like dissolves like. So what we mean by that is that polar compounds, and this could be an ionic compound or a polar covalent compound, will dissolve in polar solvents. So polar compounds and polar solvents, that's like dissolves like. On the other hand, nonpolar compounds are going to dissolve in nonpolar solvents, like dissolves like. To really drive the point home, polar solvents cannot dissolve nonpolar, and nonpolar cannot dissolve polar. So you cannot, it has to be the same polarity for it to dissolve. A great example of this would be those vis-a-vis markers you would use on the overhead projectors. They're water soluble. So the way you get that pen mark off of your transparency, and this might be dating myself even mentioning an overhead projector, is to use water to wash it off. Or if you think about the Crayola washable markers, they come right off with water. However, if your kid gets a hold of a Sharpie, that's not going to wash off because Sharpie is a non-polar solute. And if you want to get a non-polar substance off, you're going to have to use a non-polar solvent like isopropyl alcohol. It's a pro-parenting tip from me. So let's talk about what happens when we add salt, a solute, a polar and ionic compound solute that is soluble in water, to water, the universal solvent. So we start off with this chunk of salt, and once it's in water, it starts to separate or dissolve into its ions. So we will have sodium ions, which are cations or positively charged, and we'll have anions or negatively charged chloride ions. And in water, you'll see the water start to surround itself in a certain way. So water is a polar covalent compound, and the hydrogens have slight positive charges and the oxygens have slight negative charges. So what we'll see is the hydrogens with their slight positive charges are going to orient themselves towards the chloride anion, which has a negative charge, because opposites attract. And the opposite is true. We have our slightly negatively charged oxygen atoms that are turning and facing to surround that positively charged sodium cation. So they're creating what we call a solvation shell around those charged particles. So they're orienting themselves such that the opposite charges are touching each other. Okay, so we've talked about sodium chloride again, but just to kind of reiterate and zoom out of this photo for just a moment, we talked about the ability of sodium and chloride to dissolve or to separate from each other in water. So they're separating into their positively charged sodium cation and the negatively charged chloride anion. And in water, we see hydrogen with a slight positive charge wants to be closest to chlorine with a negative charge. And we see sodium with a positive charge is going to be closest to our oxygen with a slight negative charge. So we see the water orienting and forming a solvation shell around each of those ions. So What you're seeing now in the sugar water solution, and we are talking about sucrose, which is a disaccharide, and sucrose has a lot of OH groups surrounding it, a lot of hydroxyl groups surrounding it. So we have hydrogen bonding, which means we'll have some partial charges everywhere there's an OH. And what you're seeing is that sucrose doesn't separate. You don't see a separation into ions, but rather you'll see the water orient itself around a single sucrose unit. So yes, they may separate from other sucrose. You're never going to just be able to add one molecule anyway. If you add your lump of sugar, you'll see a single sugar molecule surrounded by water molecules. So they'll still form that solvation shell around it, orienting so that you have oxygens on the water with their slight negative charge closest to the hydrogens with a slight positive charge, and you'll still see a solvation shell. So it's still considered soluble. It's just not going to dissociate. All right, so what we are seeing is an organic molecule, which means it has carbons in it. That's a bad color. Let's pick a different color. Has carbons and hydrogens, and it has an oxygen and another hydrogen. So this is ethanol. Ethanol is the alcohol that we find in beer and wine. It's the alcohol we drink. And notice that it has this polar group on the end. It has a polar hydroxyl group or an OH group. And that polar group can form hydrogen bonds with water. So water is able to surround this molecule, even though it's covalent, but because it has a polar group on it, it is soluble in water. So suffice to say, alcohol is part of the solution in this case. We also see this image, so I made this image right here that you're looking at that I drew on, but this image was made using software to show what a solvation shell for ethanol would actually look like and what the distances would look like. And you can see that water can surround this molecule, making it a soluble covalent molecule. Compared to this is stearic acid. Stearic acid has a lot of carbons and hydrogens. It's very nonpolar in this entire region. And it has a tiny little polar area here. So water can surround that one little tiny end, but it can't surround this entire thing, which makes this molecule mostly nonpolar and water insoluble because water cannot surround it. There are three types of solutions you should be familiar with. So remember that we said a solution is the maximum amount, or solubility is the maximum amount of solute that can dissolve in a given amount of solvent at a specific temperature. So you can have an unsaturated, a saturated, or a supersaturated solution. And what this is referring to is how much solute is in your solvent. So if it's unsaturated, you could still add more solute to this. Okay, so it's not at the maximum amount of solute that this amount of solvent can hold. If it is saturated, the solution is considered full. It's saturated. It has the maximum number of grams of solute that can dissolve in this amount of solvent at this given temperature, which leads us to the supersaturated solution. So this is a situation where we can actually add more solute to a solution than what it can normally hold. So it's considered super saturated. It's a very unstable solution, and if you were to agitate it at all, it can, the solute will precipitate out of solution rapidly. So follow me, for example, rock candy, example of a supersaturated solution. So to make the liquid that you make rock candy from, you're going to dissolve a ton of sugar into boiling water, and you have to cool this very slowly. And what you do is you put a stick or a string into the solution. This is enough of a disruption to the solution that it's going to start to precipitate crystals out on the wooden stick or the piece of string that you have in there. On the next page, we'll talk about another example of that, but the heat packs, the reusable heat packs that you have are a good example of a supersaturated solution. So the reusable ones are kind of gel-like, and they have a little metal button or a tab inside. And in order to get them to heat up, you snap the tab inside, and it's just enough of an agitation that the supersaturated solution, the solute in there, precipitates out. So it turns into a solid. And it does this very rapidly, and you'll see crystals form inside the pack. And as it does this, it releases heat. And if you want to restore it and reuse it again, you would boil this and then set it aside to cool slowly, and you could reuse it again. Okay, so we talked about solvation when we looked at the images previously, and this is really the process of surrounding particles of the solute with solvent molecules. And so we looked at the solvation of water, but this could happen with really any solution or solvent that you have. So when you separate two molecules, we talked about the separation of salt from chloride into their ions. This can be accompanied by an energy change. Either it's going to release energy into the environment, it's going to have an exit of energy, it's going to be exothermic, or it's going to require an input of energy, it's going to be endothermic. So in an exothermic, your separation of particles as they dissolve and separate, it's accompanied by a release of energy. So it releases more energy than it takes for those particles to separate. This is how we get a hot pack. Think of calcium chloride and water. As the calcium and the chloride separate from each other, it gives off heat because the energy to separate the particles takes less heat than the amount given. In an endothermic separation, your separation of particles requires more energy than what is released. So you're going to have to absorb heat from the environment. And an example of this would be your cold packs that you might use if you get hit in the head with a baseball. Oh, that's a terrible thought. Don't get hit in the head by a baseball. Always glove up. So we use ammonium nitrate and water. And you wind up breaking your ammonium nitrate or your inner bag of water in this example, and it starts the dissolution or the separation of particles. So when ammonium and nitrate separate, it requires an input of energy from the environment. It's actually taking heat from your hand and pulling it in for the separation, and therefore it feels cold to the touch because it's taking your heat. All right, so let's talk about the products that you would expect from the dissolution or the dissolving of a substance. So looking at our first example, let me get my pen working, we have calcium bromide. Calcium bromide is a soluble ionic compound. So I'm just going to write that. It is ionic, it is soluble in water. We're assuming that we are dissolving this in water. So we would expect calcium as our cation, and calcium has a +2 charge. And we would also expect to have 2 bromide ions, each with a -1 charge. And this is dissociating in water. So we want to include water in there as well. Water is not going to separate, but this is how you would, it's an aqueous solution. You would need water present. Looking at our next substance, this is a covalent compound, okay? And covalent compounds are not going to dissociate in water. So we would expect this to stay intact. There's no separation of ions because there's no transfer of electrons. So we expect this to remain as a single unit in the presence of water. So we include water in there as well. There's no dissociation. Our final compound is sodium phosphate, which is ionic and soluble. So our polyatomic ions are going to dissociate as a unit. Remember, we always treat them as a single unit. So we can expect to have 3 sodiums, each with a +1 charge, and I'm just pulling that from my subscript. So I would expect for every, because it's a 3-to-1 ratio of sodiums to phosphate, and I would have 1 phosphate with a 3- charge. And again, remember that we're keeping that polyatomic ion intact. It dissociates as a charged unit. And again, we also want to include water in that dissociation.